Good morning.
Morning. All right. Does anybody have any questions before we get started? Now, if you've looked at the schedule, you will see that there is actually a lecture planned for Monday. That is not the normal way that we do things because the test is due Monday. But depending on how things go today, we may be able to knock out 2 of the lectures, in which case we won't need to have a lecture on Monday. And that way, if anybody has any questions or any, stuff like that for the test, then we can talk about that at that time, or you can have time to take the test at that time. That will probably happen because there's not a lot of material we need to cover between here and the end of the term. It goes pretty quick. So that should probably be the case. Does anybody have any questions about the test itself or anything like that? Okay. I do have some people who have turned in the redocs and the activity series. My plan is to have those graded today so you can have that feedback back before you have to take the test. Shouldn't be a huge issue. So, and I will be giving feedback in the sense of here's what I saw, here's like what step I found problems with, and therefore, you made this mistake here and that led to these things below it. And so if anything like that happens. So again, I should have those done and you'll get feedback sheets that show the actual steps for the balancing for all of those things, as well as where I saw differences in what you did. So that's how that grading should go. You should get a feedback sheet that goes with that. Anything else? I'm trying to think if there's anything else. I did post the grades for exam 1. You should be able to see those. If you haven't seen those, please let me know. And I had forgotten to extend the surveys for the 2 labs that are due on Sunday. So I went in and took care of that this morning. Thank you for reminding me because I had a student that reminded me of that. So that has been taken care of now. I think that's everything. Okay. All right. So let's get started. So we're going to change gears. We're going to talk about thermodynamics. So thermodynamics is the study of where energy moves things. That's what that term means. So we're going to start in chapter 6 with what we mean by the nature of energy and the types of energy that we deal with. We'll talk about energy changes in chemical reactions. We get an intro to thermodynamics, and then we'll start talking about enthalpy. So that's the first type of thing that we're going to talk about in this series. So questions on where we're going? Awesome. Now, a note about this lecture. This material tends to be very, very dry. It's a lot of definitions. There aren't a lot of things that we're going to have to calculate, especially until we get into some other stuff. So, and all of the calculations that we do for enthalpy, entropy, and free energies, so these things that we're going to be talking about, are all basically the same. So it's going to be a lot of repetition. All right. So there's not a lot of practice problems that we're going to do for this material on its own. It does play a big part in what we do later. So it's important that we understand what's going on. So this practice for this chapter will be short. So this particular lecture will be like define these terms, tell me the sign conventions, that kind of stuff. So it's unfortunately kind of boring. I apologize. Now, nature and the types of energy. Now, this is a lot of physics stuff. I really didn't like the overlap, but energy is the capability to do work. Okay, so that's the capacity to do work. There are several times things that we talk about. So things that get talked about, radiant energy, which is solar energy coming from the sun, heats up the atmosphere, the Earth's surface, and stimulates vegetative growth and climate patterns. Okay, so that's one thing. We don't spend a lot of time with that. Thermal energy is the energy associated with random motion of atoms and molecules. That is important, directly related to temperature. So that's how we measure temperature, is based on that thermal energy. Energy is a function of both the amount of material and its motion. Okay, so larger masses have a higher amount of energy just because there's more material. Then there's chemical energy, which is stored within chemical substances. It's what is released during chemical reactions, during bond breakage. It's what's stored during bond formation, and it's converted to other forms during those processes. So sometimes not all of the energy goes from being stored to being used to make new bonds. Sometimes some of that energy is given off as heat or has to be taken in as heat to make that work. Okay, so that's where we get some of that stuff that comes with that. There's also potential energy. Typically, when we talk about potential energy, this is something we talk about in physics. Is the energy available based on the position of a material? And so either in relation to how high it is, so how, a larger fall creates more energy, or based on the structure of a molecule. Okay, so there is potential energy based on the structure of a molecule. Now, we do have a law of conservation of energy that states that the total quantity of energy in the universe is assumed to be constant, and it is. Energy is neither created nor destroyed. It's only converted from one form to another. Okay, so we don't make it, we don't destroy it. It gets converted from one form to another. Okay, so just like we can't suddenly make mass out of nowhere, we can't make energy out of nowhere. It has to come from somewhere and go somewhere else. Okay, so there's that part of it. Any questions on our definitions so far? Okay. Now, most chemical reactions involve the exchange of heat. So thermochemistry is the study of heat change in chemical reactions. So thermochemistry. Heat is the transfer of thermal energy from a material higher in energy to one in lower in energy, usually measured by the temperature of that material. Now, when we talk about these things, we have to start talking about some phrases that we haven't really used yet. One is the system. And that's whatever we're actually interested in looking at. We can define it in any way we want, but what we're looking at is called the system. Everything around that system is called the surroundings. So it's anything outside of our system. So we often define our system as this chemical reaction that's happening, and our surroundings as being anything that's around it that it could either give us energy or take energy from that. Okay, it's important to understand that those two things are not the same. So we talk about energy being given off or taken in from the surroundings. All right. And there are three types of systems that we can talk about. One is called an open system, which means it can exchange mass and energy with the surroundings. This is typically how we operate. Okay, we can exchange mass and energy with anything around us. But under lots of conditions in the laboratory, we will try to close that down to isolate those things so that we can study them just in context of what they're happening. And we can do that in two ways. One is a closed system, which allows heat to transfer, but not mass. So we can allow heat to go out or in, but no mass can be transferred outside of that system. Okay. Or it could be isolated. And that means that we can't, that nothing is transferred, either mass or energy. And so we can isolate a system both thermally and with mass so that we can study what happens just within that system and not with anything else. Okay, so that's three different ways that we can talk about this. Understand that a lot of the measurements that we have for the energies that are involved in this are done either in closed systems or isolated systems so that we're sure that that energy comes from the system under study. Okay. Now, there's also heat transfer that we have to talk about, and we've actually already talked about this a little bit. We talked about transfer of energy from the system to the surroundings, and that is an exothermic process. So heat is a product that's given from the system to the surroundings. Okay, so that's exothermic. We've also talked about endothermic, where energy is taken in by the system from the surroundings, and therefore heat is a reactant in that system. Okay, so that heat transfer is important. Whether it's endothermic or exothermic can be important in determining whether or not something can happen, because we either need to be able to give up energy to the system or take energy from the system to be able to do that. And if there's, if it's too hot, we can't give up that energy. And if it's too cold, we can't take in that energy. So it depends on whether it's endothermic or exothermic, whether that is favorable to being able to do that reaction. Okay. So that energy transfer is important when we consider the systems in question. Right? So that's why we've started to see that. We've seen that a little bit. We talked about that when we were talking about chemical reactions and rates, things like that. So we saw it there in those rate diagrams that we looked at. This is the other place where we start talking about that. Okay, so we'll talk about it in a lot more detail here. So questions on any of that? All right, when we talk about thermodynamics, scientific study of the interconversion of heat and other forms of energy, that's what thermodynamics means. We study the state of the system, right? So the state has to do whether it's isolated or closed or open, right? So that's part of it. It has to do with the composition of the system, the energy of the system, temperature, the pressure, and the volume. Those are the things that we consider when we talk about the state of that system. State functions are properties that are used to determine the state of the system, no matter how I got there. So things that we talk about, volume, temperature, pressure, energy, okay, all of that is related to that. And so if I specify all of those things, that gives me a complete picture of what that state looks like for that particular system. All right. Now those state functions, because it doesn't matter how I got there, all right, that's an important definition of how we can look at that, because it doesn't matter which pathway I took to get between point A and point B. All it matters is that I got to this place where the system is currently living. Right? So that's important. So state functions are independent of pathway for how I got there. It's not important how I got there. It just matters where I am. All right. So those are things that we talk about in terms of the state of the system and the things that determine that system. All right. Now, our first law of thermodynamics says that energy can be converted from one form to another, but neither created nor destroyed. And energy has two main components that we consider in chemistry. One is the kinetic energy, the molecular motion and movement of the electrons in the molecules. That's one. The second is the potential energy, which is the attractive interactions between electrons and nuclei and repulsive interactions between nuclei and electrons and between individual molecules. Okay, so there's attraction and repulsion that happens within that potential energy that exists. Okay, so both of those things are there. But those are the two components that we typically talk about when we talk about energy in chemistry. All right, so kinetic and potential. Measurement of all forms of energy is extremely difficult to do. Very, very difficult. The changes in energy can be determined experimentally. So it's very difficult for me to say, hey, this has an absolute energy of, whatever value. But I can look at the differences between things fairly easily. I can measure those differences fairly easily. All right. Potential energy, U, is our measure of these things. So we know that the change in the U, the potential energy for the system, is equal to the negative of the change in the energy for the surroundings. Okay, since energy can neither be created nor destroyed, any change that happens within my system has to have come from the surroundings. Okay, so that's where that has to have come from. And so it's the same magnitude, the same size, but the opposite sign. Okay, potential energy change in the system is equal in size, but opposite in sign to the change in the universe. And if a system goes from high potential energy to low potential energy, like a stone falling off a cliff, then the surroundings gain that energy that was given off by the stone. So if I give up energy, that goes to the surroundings. If I need energy, then it has to come in from the surroundings. Can be in a different form, right? So it's not necessarily the same kind of energy. We're more interested in what happens to the system. Okay, so I'm not so concerned about what happens to my surroundings. I'm more concerned about what's happening within that system. And so when we talk about that change in energy, we're often looking at that in terms of two factors. One is Q, the heat exchanged between the system and the surroundings, and W, the work done by or to the system. Okay, so those are the two factors that we look at. Right? Q is energy, W is work. All right. So those are the things that we're mostly concerned about when we talk about the energy within our systems. Okay. Now, when we talk about heat, so that Q, it's transfer of thermal energy between system and surroundings. This is not a state function. Okay, it depends on the initial state, it depends on the final state, but it also depends on the path that we use to get between point A and point B. Because if I take a really, really long circuitous route to get there, then I use a lot more energy. So that pathway is important. Heat absorbed by the system is positive. Heat given off by the system is negative. Okay, so that's a portion of what we're looking at. Now, the change in potential energy, U, is equal to the heat and the work. So that potential energy is given by the heat and the work. Those are the two things that we have to consider when we look at that. Now, the work is the energy transfer that is used to do something other than changing the temperature. So things that we consider, this is not a state function because it depends on the initial state, the final state, and the path again. So work done by the system. So work done on the system by the surroundings is positive. Work done by the system on the surroundings is negative. Main types of things that we see: mechanical work, so compression by changing pressures. That's one thing. Okay. Electrical work, things that are done by redox reactions. That's a type of energy that we look at. That's a type of work that we talk about. And surface work, which is related to the intermolecular forces. So if we're getting energy that's related to, say, the rise of a liquid in a capillary tube, there's work that is done there. And so that's something that we can talk about because it's based in that surface interaction that happens there. Right. So those are the kinds of work that we talk about. We also have mechanical work, so expansion and compression of gases. So that work is typically described as negative P times the change in volume. So it's equal to the negative of the pressure times the change in volume, because that's typically what we're seeing is because of that change in volume, we're getting work done. Okay, so that's how the mechanical work typically plays into this. All right. So questions about any of that? When we talk about the enthalpy, the energy of chemical reactions, if we can keep the volume constant, the change in internal energy is only related to the change in heat. So that delta U, which is equal to the Q and the W, if it's equal to Q minus P delta V, which is what we just described for W, then if we keep those volumes constant, then delta U is equal to the Q. Okay? Since delta V is 0, then we only have that QV, or the heat change at constant volume. So this is how we tend to try and measure this, is to try and make it show that that volume cannot change, and therefore we're measuring only the heat involved in that. Okay? Since that's nearly impossible to do, it's really, really complicated. We now define a new function of a system called enthalpy. Okay, and that enthalpy, instead of being U, is equal to H. And that's equal to that U plus PV. Okay, so U is the internal energy, P is the pressure, and V is the volume. right? And H is this thing called enthalpy, right? That's what we're actually going to be able to measure because that we can reliably get, right? Now U, that internal energy, P, the pressure, and V, the volume, are all state functions. Okay, so those don't depend on that pathway. They just depend on where I start and where I end. And because of that, H, that enthalpy, is also a state function. And if we're able to hold that pressure constant, then you get that delta H is equal to delta U, the change in the internal energy, plus the pressure times the change in volume. Okay? So if you're able to hold that pressure constant, then we can get to a phrase that looks like this. All right? So that means that we can look at what is the change in the internal energy based on where the pressure is and any change in volume that we happen to see. Okay? Cool with that. And when we talk about the enthalpy of our chemical reactions, since most chemical reactions are constant pressure, we can equate the following. Delta H is equal to the H for the products minus the H for the reactants. Okay, so if delta H is positive, the reaction is endothermic. Heat is absorbed by the system from the surroundings, and heat is a reactant. If delta H is negative, the reaction is exothermic. Heat is released by the system to the surroundings, and heat is a product. Okay. Now, in both cases, we see effects of Le Chatelier's principle from the heat. So if I raise the heat, and I'm supposed to give off heat as a product, and if I raise that heat, then it shifts the reaction back towards the reactants because I'm less able to give off heat in that case. So Le Chatelier's principle does apply here. So again, any changes in exterior temperature will have an effect on where this reaction can go based on whether it's supposed to take in heat or give off heat. Okay. Thermochemical equations show both the mass relationships and the enthalpy changes. So what do I mean by that? Well, here's one reaction. I have CH4 plus 2O2 goes to CO2 plus 2H2O. And I know that the energy for this is 88 kilojoules per mole. Okay. If I look at H2O for solid going to H2O liquid, the delta H for that is 6.01 kilojoules per mole. If I were to multiply that equation by 2, and I get 2 H2O solid going to 2 H2O liquid, the delta H doubles. So this is different than what we did in our electrochemistry. Remember when we did redox, we didn't change those values. Here we have to change those values because it's dependent on how much mass we're doing this for. Okay, so that's important. It's different between those two places. And if I were to reverse this reaction and go from liquid to solid, we're now looking at that delta H being negative 6.01 kilojoules per mole. So it's dependent on which direction it's going. That determines the sign and what the numbers out in front are. So if I multiply them by 2, I have to multiply this value by 2. Okay, so the stoichiometry in this reaction is incredibly important. Now, this goes back to how we were balancing equations in the first part of chemistry. So remember that you were probably told that the preference was to have it not be fractional values. And that's because these are tabulated, for most of these things, with whole numbers. So if you want to use those fractional values, you can do it, but you've got to change these numbers based on it. Okay, so that's why that was important. So it matters what that stoichiometry looks like to determine what these values are. So you have to make sure when you look up one of these values that it matches the stoichiometry of the reaction that you're looking at. And if it doesn't, then you have to modify the energy that's associated. Okay, so remember to multiply or divide as appropriate per the stoichiometry, and that the sign is dependent on which direction this reaction is going. Okay, so that's the differences we've been talking about so far. Now, does that make sense? Okay. Now, some practice. We have some standard enthalpies of formation of some inorganic substances at 25 degrees. I stole this from a textbook. I don't even remember which textbook this is from, and I didn't actually list it, so that's terrible. So this is just a table from one of those things that we were looking at. All right. These are the delta H naught F, so the heat of formation for these materials. And I want to calculate the enthalpy of reaction for the following chemical reactions. So I want to look at the formation of 4 moles of Al2O3 solid. Okay, 4 moles Al2O3 solid. So I'm looking for Al2O3 solid. So I come over here and I say, okay, is there some place in here that I see that? And that actually is right here. So I see Al2O3 solid right there. And the heat of formation that goes with 1 mole of that Al2O3 solid is negative 1669.8. So negative 1669.8 kilojoules per mole of Al2O3. So I know that that's what that table reads. Now, if I want to do this for 4 moles of that material, then I need to multiply this by 4. So if I want 4 moles of Al2O3 solid, then I need to multiply by those 4 moles so that those will cancel, and I will end up with an energy that is associated with the formation of 4 moles of Al2O3 solid. So let me find my calculator. I know it's here somewhere. So I take that negative 188, or sorry, 166, 669.8, and I multiply that by 4. And that's how much energy it would require for me to do this. So negative 6679.2 kilojoules. And that is in kilojoules because I've canceled all of my other units. So that's how much energy it would take to form that. Now, since it's exothermic, that is actually being given up by the system to the surroundings when I make that material from Al and O. Okay, so that's what I'm looking at. Questions for that? Now, the next thing it asks, why is the heat of formation for F2 gas equal to 0? So if I come down here and I look at F2 gas, F2 is right here, right there, and its value listed is 0. And the question becomes, well, why is it 0? Looking at this table, I see a couple of things. I see a number of things that are in there, what we would call ground state, the state that they exist in nature. So H2 gas, F2 gas, Cl2 gas, Ca solid, C graphite, Al solid, Ag solid, Hg liquid, I2 solid, Mg solid, N2 gas, O2 gas, and S in the rhombic. So it's the type of crystal structure that it has. All of those are 0. And that's because they exist as they exist in nature. So their energy has been given as 0 because I can't really actually measure what its absolute value is. I can just measure changes from how it exists in nature. So all of those values are 0 because that's how they exist in nature. So if you're looking for something as you typically see it in nature, that value for its delta H naught F, the standard heat of formation for that material, should be 0. So that's why. Okay, does that make sense? Now, why is it that the heat of formation for H gas is not the same as H2 gas? So right now we're talking about the difference between this line right here and this line right here. And my question is, well, why aren't they the same? Well, because it takes energy to break the bond between those two hydrogens. H2 exists as a dimer because it's the most stable way that it can exist because it doesn't have enough electrons. So if I want to break the bond between the two of them, I have to put in energy to do that. So that's why this H gas has this number that's associated with it, because I have to put in 208.2 kilojoules per mole to break that bond. So that's the energy associated with breaking the bond. All right. So that's where that comes from. Now, the next thing it says is the formation of HF gas from H gas and F2 gas. Okay, so I want to calculate how much energy does it take to make HF as a gas from H gas plus F2 gas. So the first thing I see is that this is not balanced. Okay, so the way that I've written this, I need to make sure that I have two H's to deal with this, but it wants me to do it from the H gas, so I need to have two of these to do that. And I need to make two HF as a product. So that's the first thing I needed to balance that equation. The next thing that it says is that previously, I saw on this slide, that we take the energy of the products minus the energy of the reactants. That's how I calculate that. So if I'm looking at this table, I need to look up the values for each of those things. So the value for this H, we saw this as 218.2. The F2 was 0. Okay. And now I need to find HF. Okay, so is HF on here? Yes, actually it is. So HF gas is negative 268.61. And those are the values as listed. All right, so if I want to calculate the energy that's associated with this, and the way that I symbolize that was as delta H is equal to the sum of the reactants, and they need to be multiplied by the stoichiometric coefficients. So I need to take the 2 times the negative 268.61. I then need to subtract the 0 for the F2 plus 2 times the 218.2 for the H. Okay, so as written, that's how this would look. All right, so again, this is my 2 times the HF, this is the F2, and then this is 2 times that H gas. Okay, and so I can calculate that value. I mean, fairly simple for me to do that. Oh, wrong number. Got ahead of myself, sorry. I apologize. Okay, so 2 times the negative 268.61 minus the quantity of those two reactants that we have. I'll go ahead and close that parenthesis, and that should give me the value that I need. And so that tells me that that energy is negative 973.62 kilojoules. Okay, and that's for this particular reaction. So it's not a per mole because this is not for 1 mole. This is for 2. So that's why I don't list it as a per mole. This is just the energy associated with this reaction. Now, does that make sense? And again, things that I remember from this is exothermic, so it's giving off energy when it does this process. This would be a product for my heat. So it gives off energy when I do this. So it's, energetically favorable to make HF out of H and F2. All right. So questions about that? And asks about the formation of AlCl solid from Al solid and wrong direction. Sorry. From Al solid plus Cl2, which is a gas. I will need 2 of those. That will then give me 2 AlCl, which is a solid. Those would be the values that I would look up. So my Al solid again is 0. So if I want the delta H for this reaction, that's equal to my products, which is that AlCl. And do I see AlCl in this table? I hope so. Actually, I don't see it in this table. Well, that sucks. Because without an actual value here, I can't do that. Now, I could change this and make this an AG instead if I wanted to do it that way, because I have that value. But because I don't have an AlCl value here, I couldn't do this reaction as it is written.
Is AlCl not the second one?
Is AlCl not the second one? The second one right here, this is AgCl.
Oh my god, sorry.
No, it's okay, because I probably was looking at that too. And that's why I said I could change it to AgCl, but it's not. So if you don't have a value for it, based on what we know, we can't do that. So I would say that I cannot solve this using the information that I have. It's just not possible, because I need to have some idea what that energy for the product is before I can do this. So there's that. Now, the last one says, how much energy does it take to change from the rhombic form of S to the monoclinic form? So you can see that you have the rhombic form right here, and that's 0, and the monoclinic form is 0.30. So it takes 0.30 kilojoules per mole to go from one to the other, since I'm just taking this minus this. Okay? So does that make sense? Now, you are limited by the information that is tabulated for you, and that can be problematic, right? So we used to provide large tables in the exam handouts of a lot of these values. We found that that was complicated. So we are now making smaller tables that are available to you within the test. So you will find the values that you need within the test rather than the exam handouts that you've been given. Okay. Now they may not be exactly where you think they should be. So remember to look through the test to make sure that they're not somewhere. Don't assume that they are not present on the test just because they're not exactly in the question, because they may not be exactly in the question. Okay. So questions about what we did or why we did it. Okay. Now, when we talk about the comparison between delta H and delta U, okay, so the internal energy versus the enthalpy that we're measuring. Since there is work done if the volume changes in a reaction, the internal energy and the enthalpy are not always equal. They're not always the same. Okay, the values are similar, but they can differ in the amount of work done by the change in volume. So you may see that in, if you're out on the internet, you may see that. That's not something we'll talk about here, but that is something that can happen. Typically, if there is a change in volume, we can calculate the difference between delta U and delta H using this equation. Delta U is equal to delta H minus RT delta N. Okay, so that's the gas constant times the change in temperature in Kelvin times the difference in the number of moles of gas between the product and the reactant. Okay, so you can calculate that. So that's something you need to be aware of, because if you're working somewhere and we're talking about differences and all you can get is a tabulated delta H, but you need to know what the actual internal energy change is, you can calculate it. Okay, so there is a way to do it, but it is not something that we are going to specifically discuss. I'm more concerned that you know how to calculate delta H, because if you need to calculate delta U from delta H, your friend Google can help you. Okay? So does that make sense? So things that we can do with the information that we've been given. All right? Given the following information, calculate the heat involved when 87.9 grams of SO2 is converted to SO3. So we're given a balanced equation. 2SO2 plus O2 goes to 2SO3. And the delta H for that reaction is negative 198.2 kilojoules per mole. Okay? So that's the energy that's associated with this particular reaction. So if I wanted to know how much energy it would take for 87.9 grams of SO2, the first thing I need to do is convert that to mole. So I take that 87.9 grams of SO2, I divide that by the molecular weight of the SO2, so the 64.07 grams of SO2 per mole of SO2, and that gets me to moles of SO2. From that, I can take that this relationship is negative 198.2 kilojoules per mole for the formation of 2 moles of SO2, because that's what's in this balanced equation. There are 2 moles in this equation. So I put the 2 moles down here and this negative 198.2 up here. And so then I can do this calculation to get negative 136.7 kilojoules based on that equation. Okay, so the thing that you need to see from that is that not only do you need to use the enthalpy for this, but you need to make sure that you've corrected for the number of moles of SO2 that are within that reaction. Right? Now, it says to calculate the change in internal energy when 2 moles of CO are converted to 2 moles of CO2 at 1 atmosphere and 25 degrees C. So we take 2 moles of CO gas. Okay, when I take those 2 moles of CO gas, I have to add O2 to that to get 2 moles of CO2. So that's the balanced chemical equation that we're looking at for this. And the delta H for that is negative 566.0 kilojoules per mole. Now, if I were going to calculate the delta U for this, I would need to take that delta H and then put in this correction factor, the RT delta N. So looking at the delta N, I have 3 moles of gas on this side, 2 moles of gas on this side. So that means that my change is negative 1 moles. Okay, so I take that to calculate delta U. I take my delta H that is here, the value that I was given. I subtract the 8.314 joules per Kelvin, which is R, times the conversion factor, 1 kilojoule is 1,000 joules, because this is in joules and everything else in my equation is in kilojoules, times 298 Kelvin, because we're doing this at 25 degrees C, times negative 1. And that means that that delta U for this change would be negative 563.5. So I've shown you how to do one of those calculations. I will not expect you to do this on a test. But I wanted to show you what that looked like to make sure that I showed you how we get the number of moles over here. So the 2 plus the 1 is 3 minus the 2 over here, which is negative 1. So it's products minus reactants, 2 minus the 3, it gives me negative 1. And then putting in the delta H, the R, and the correction for the R, because it's always in joules rather than kilojoules, which is what our energies are in. Okay. So remember, when we're doing these things, we have to make sure that we're in the same energy units. Okay? So questions about that? Okay. So some additional practice. If I have 2 H2O solid going to 2 H2O liquid, and we had that in the table as 12.0 kilojoules per mole when we multiplied it by 2. How much energy is required to take 42.42 grams of water from solid to liquid? So that's something I want you to calculate. And I'm going to give you a couple of minutes to go through these calculations, and then we'll talk about that. Okay. And how much energy is released when the same amount of water is frozen to ice? So that's the second part of that question. Then we have this next question, given CH4 plus O2 goes to CO2, and there's something missing there. There's no water there, and there should be water. Oh, there's H2. There's 2 H2 gas. I wonder if I calculated the value correctly. Hope I did. Let's assume that I calculated delta H correctly and I forgot the H2 there, because knowing me, that's what I did. Sorry about that. What is the energy when 68.32 grams of CH4 from CO2, assuming that a similar amount of O2 gas is formed? Why does that say O2? It should be H2. What is the amount? I'll tell you what. I will post this one once I've fixed it, because I'll clean it up. So let's talk about this. Let's have you guys take 3 minutes and see what you can do with this calculation. Okay. So as I looked at before, I need to take this mass of H2O that I have, and I have to convert that to moles. So the molecular weight of H2O is 18.015 grams per mole. So I take that 42.42 grams of H2O, I divide that by the molecular weight, 18.015 grams per 1 mole of H2O. And that'll tell me how many moles of H2O that I have. I can then take and look at this in terms of their 12.0 kilojoules for the formation of 2 moles of H2O. Because again, there were 2 of these, so I need to convert this to a single mole per H2O. So that's why I have to look at that way. So I take that 42.42 divide that by the 18 that I calculated, this guy right here, and multiply that by the 12, and then I divide that by 2. And that gives me 14.13 kilojoules. Okay, so that's how much energy it would take for me to convert that amount of solid water to liquid. Okay, so I've taken everything into account by doing that. Now, if I wanted to go the reverse direction, I know it's the same calculation, it's just opposite in sign. So I don't actually have to calculate this. So this is solid to liquid. If I wanted to go liquid to solid, I know that's negative 14.13 kilojoules. Because it's the reverse of that reaction. So when I reverse that, I just change the sign on the energy. Okay? So does that make sense? So anytime I have a tabulated value, something that's been given to me like this, I need to make sure that the number of moles that are here is equal to what I'm trying to calculate. So if I'm looking for 1 mole, I would need to divide this energy by 2 to make that happen. Okay? Like I said, I will post the other one as soon as I fix it. So questions on what we've done. So things I might ask you about what we've talked about so far. So what is a state function? The answer that I'm looking for there is something that is not dependent on pathway. So that's what we talked about. So matters where I start, matters where I end, does not depend on the path by which I get there. If I wanted to name one of the state functions, we listed a couple: pressure, volume, and delta H, or enthalpy. I'll take the delta because it's H, are all parts of that. Okay, so those are things we listed that way. What is an isolated system? Okay, so we had 3 definitions, had to do with whether I could transfer mass and energy. Isolated, I could transfer neither. So no transfer of energy or mass. So isolated was nothing, open was everything, and did I get that backwards? Hold on, let me double check. I love talking myself into a circle. Pretty sure isolated is nothing, and then closed is just not transfer of the energy portion or the mass portion. So you can transfer energy, not mass. Come on, move. Are you really going to be this one? I love it when I'm trying to find something it doesn't want to cooperate. Oh. Give me 2 seconds. doing? Sorry, my tablet froze. Apologize. I hate it when this happens. Okay. And again, verifying the information I was looking at. So isolated does not allow heat or mass to transfer to the surroundings. So just wanted to make sure that I had not talked myself into a circle. So, and that was back here that we were talking about. Exothermic and endothermic. My exo, I give off energy to the surroundings. And that is negative. So that's the sign convention. That's what I mean by that. My endothermic, I have to take in energy from the surroundings. And that is positive. So again, endothermic heat taken in, it is a reactant. Exothermic heat given off, heat is a product. So combustion methane, CH4, releases 890.4 kilojoules per mole of heat in the reaction. So CO2 plus 2H2O gives me CH4 plus 2O2. How much energy is given off when 2 moles of CH4 are burned? Okay. So if I release that much energy for this reaction, so if this reaction here, as written, CO2 plus 2H2O goes to CH4 plus 2O2 has a defined heat of 890.4 kilojoules. Okay. If that is how that is defined, and I want to talk about the CH4 being burned, so the opposite side. So I'm reversing this reaction for 1. So now we're going from CH4 plus 2O2 to CO2 plus 2H2O. That energy is going to be negative 890.4 kilojoules. Okay, so I flipped it, so I need to change the sign. But it's also for only 1 mole of CH4. So if I'm going to multiply this whole thing by 2, then I would need to double that value. And of course, we all know I can't do that math in my head. So And that's 1780. And it's still negative. 1780.8 kilojoules for 2 moles. So again, because I flipped the reaction, I changed the sign, and then when I did it for 2 moles, I needed to double that up. Okay? So that's the first part. How much energy is released when 22.4 grams of methane are burned? If I want to look at 22.4 grams, then let's let up 22.4 grams of CH4. Molecular weight on that is 12.011 for the carbon plus 4 times the 1.008 for the hydrogen. Yes, I had those memorized off of the table that I give you guys. So that's 16.043 grams of CH4 for 1 mole of CH4. And then if we're looking at the reaction for 1 mole of this material, it was 890.4 kilojoules for 1 mole of CH4. So taking the value before I multiplied it. So that way I'm only looking at 1 mole of CH4. So I can do that math. 22.4 divided by the molecular weight there times the negative 890.4. And that gives me negative 1243.21. How many sig figs should that be? Technically speaking, that should be 3. So I would report this as negative 1240 kilojoules. So 3 sig figs, I would report it as 1240. Okay. So that's for 22.4. Now, if I make 45 grams of methane from carbon dioxide and water, so that's the initial reaction here, and I'm looking at 45 grams of methane. So I have 45 grams of CH4. I still have 16.043 grams of CH4 in 1 mole of CH4. But the energy for that, the formation, is 890.4 kilojoules per mole. Because again, that was 1-to-1, so there's 1 CH4 here. So that's what I need. And it's positive because it's the other direction. Then I can do that math. So 45 divided by 16.043, and then I can multiply that by the 890.4, and that gives me 2497. And again, 3 sig figs because I have 3 sig figs in the number that I started with. So 20. I'd report that as 2.50. By the time I've rounded it, 2.50. And I do this just because I didn't want to lose clarity on how many sig figs it should have. So I could report it as 2500, but if I do it that way, then it's not clear how many of those sig figs are significant. So that's why I would report it as 2.53 times 10 to the third to make sure that it's clear that I only have 3 sig figs that are there. That's the only reason I made that choice. So cool with that. Now this last one, what is the heat of formation for this reaction? 2NO gas plus O2 gas goes to 2NO2 gas. If the delta H not F for NO is 90 kilojoules per mole and NO2 is 34.34 kilojoules per mole. Okay. So that's the first thing that I asked. So if the reaction for 2NO plus an O2 And they've given me a delta H for NO as 90 kilojoules per mole, and the NO2 as 34 kilojoules per mole. Then I can calculate the delta H for this. Heat of reaction if 1 mole of NO is made from NO2, right? So as written, I want to calculate what it is as it's written. That's the first thing they asked me. So in that case, I have 2 times my product, which is the 34 kilojoules per mole, minus the 2 times the 90 kilojoules per mole, minus the 0, because remember that this one is in its form as it appears in nature, so that one is 0. So if that is the case, I have need the mouse. Where'd the mouse go? There we go. 2 times 34, and then I will subtract 2 times the 90, and that gives me negative 112 kilojoules for that particular reaction. It then asks me what is the heat of reaction if 1 mole of NO is made from NO2, okay? And that's because that's half of the reaction, and it's reversed because we're going to the NO. So I'm going to reverse that direction, and so then we're going to be talking about a positive 112, but that's for 2 moles of NO. Okay. Then if that is the case, then I need to divide this by 2 in that direction. So 112 divided by 2. So, and it's positive 56. So again, because I reverse direction, it's positive, and because it's only half of that reaction, that's NO. Okay? So does that make sense? So these energy work in much the same way as lots of the conversion factors that we use in general chemistry. So we're just looking at our stoichiometry, getting to the number of moles of these materials that we have, and multiplying this energy per mole to get that total amount of energy that we need for this process. Okay, so your unit should help you with that. So don't forget. So any questions on what we've talked about? Now, there is going to be some homework that I'm going to post. I was finishing it this morning, so I haven't posted that yet. What I'd like to do at this point is start talking about that next lecture so that we don't have to talk on Monday. That's not the one I wanted the other. So any questions about what we've talked about so far? Okay. So now we're going to talk a little bit about some of the other things we do with these energies. And there are some other things that we do. One is calorimetry, which is how we measure these energies. One is to talk about the standard enthalpy of formation and reaction, which we talked a little bit about. And then we'll talk about the energy that's associated with phase changes. Because again, we didn't really do that in 110. So now we have to talk about how we do that. Okay. So just a couple more things that we're going to talk about. We may finish this, we may not. When we talk about calorimetry, one of the specific things that we talk about is specific heat. And that is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree C. So it's joules per gram degree C. Okay. So every substance has a specific heat that is characteristic of that material. It's how much energy you need to be able to raise that thing by 1 degree. Okay. And a heat capacity, which is, so specific heat is symbolized as S. Heat capacity is symbolized as capital C. is the amount of heat required to raise the temperature of a given quantity of a substance by 1 degree Celsius. Okay, so again, it's joules per gram degree C. So if I wanted to look at the heat capacity for something, I would need to be able to look at how much of that material I have times its specific heat. Okay, so we can calculate that energy by looking at how much of it we have times the specific heat of that material. Okay, and if we wanted to look at the heat transfer that's involved in that, that's C times the change in temperature. Okay, and so that's the mass of that material times its specific heat times the change in temperature. That gives me the energy involved in making a temperature change for that material. Now that's important, and then we understand that that's how those work together. Because if we're doing something called constant volume calorimetry, we can measure something called the heat of combustion of a reaction, or the heat of a reaction can be measured in a machine like this one that we're showing here. And what this is called is a bomb calorimeter. So it's closed so that we can't change the volume of this thing, and it's isolated. So this is an isolated system, can't transfer heat, can't transfer any of the mass. So we can measure the energy that's associated with combusting something. So if I burn it up, how much energy does that take? Okay, so that's why we measure heat of combustion in this. It's a closed system, has constant volume. The change in heat, the Q for the system, is an indicator of the energy of the reaction. And so the Q for that system is equal to the energy for the calorimeter. So there is some energy that's sucked up by the calorimeter itself, plus the energy of the reaction. Okay, so QCal is the specific heat capacity of the calorimeter, and that can be measured experimentally. Okay, so we can go in and do a known reaction that has a specific energy associated with it and see how much the temperature changes to measure what the heat capacity for that calorimeter is. And so once we know how much energy is going to be sucked up by the calorimeter, any other change that we see is based on the reaction and the energy that's left over once we've taken care of the calorimeter. Okay? So we can measure the Q for the calorimeter as the C, the heat capacity for that calorimeter, times the change in temperature. And that C for the calorimeter is measured as the Q for the calorimeter divided by delta T. So if we use a material with a known heat of combustion, so it's just 1 gram of benzoic acid is 26.42 kilojoules, and measure the temperature change, we can solve for that C cal for that. Okay, so that is not a measure of delta H, or that is a measure of delta U, not delta H. Okay, so it is the complete change in the internal system as opposed to just the energy of that. Okay. But this is one of the ways that these values get tabulated, is to put them into devices like this. Now, it used to be in the laboratory, we would go in and do an experiment like this, but the virtual lab that you guys are going to do will have you measure the heat for a stacked styrofoam cup calorimeter, and then measure the energy for the neutralization of an acid-base reaction. So not exactly a bomb calorimeter, but it's similar in nature. Right? So that's what that lab is about. So that's what we're doing with our calorimeters. So we can also do constant pressure calorimetry, and that can be used to measure the heat of a reaction for non-combustible reactions. So if it won't burn, we can do it this way. Okay. Since it's constant pressure, the Q of the reaction is equal to the delta H. Okay. So Q calorimeter equals 0 for this calorimeter, so we're going to ignore it. All right. And we can determine the heat capacity for an added component. Okay. So that's similar to what we'd be talking there. The heat of reaction can be determined using a method similar to example 6.8. All right, and we're going to see that in just a second. I thought I had flipped this. Oh, good. Oh, this is the wrong one. That's why. Give me a second. Sorry, I pulled up the wrong thing because I flipped it. Not in this particular one. I have to get it right. Oh, there it is. Oh, it didn't stay flipped. Well, that sucks. So I apologize if this is sideways. I'm very sorry about that. Here you go. Really? Technology is not my friend today. Okay. So like I said, I apologize if this is flipped. But we have a lead pellet having a mass of 26.47 grams at 89.98 degrees C. It's placed into a constant pressure calorimeter of negligible heat capacity containing 100 milliliters of water. Water temperature rose from 22.5 degrees C to 23.17 degrees C. What is the specific heat of the lead pellet? So we're looking at this lead pellet that's 26.47 grams. And that was placed into this constant pressure calorimeter. And we had 100 grams of water. And the change in temperature goes from 22.5 degrees C to 23.17 degrees C. Okay, so the temperature's gone up slightly. Now, and they want to know what is the specific heat for this lead pellet. So the specific heat, grams, joules per gram degree C. Yeah, that's what we're looking for. So we know that this is what we're looking at. We have this 100 grams of water. It's gone from 22.5 degrees C to 23.17 degrees C. And we put this into it. So 26.47 grams. We've gone from 89.98 degrees C for the lead pellet down to this final temperature, which is right here. Okay. So I know that we have the heats for both of these two things and that they're equal to each other because whatever's given off by that lead pellet is taken up by that H2O since the calorimeter is negligible. So I know that's why these two things are equal to each other. So that's why it says right here that they're equal. Okay, so what's given off by the lead pellet is picked up by the H2O, but it's opposite in sign. So I can look at the H2O and I can say that that temperature change is based on the mass of that water times the specific heat of the water times the change in temperature. Because that's how we talked about this. Okay, so that energy is going to be equal to the 100 grams times the specific heat of water, which happens to be 4.184 joules per gram degree C. And that is a tabulated value that I could look up or that you could be told. So either one of those things could be true. Most likely, that will be something that you will look up. It is in the exam handouts, if I'm not mistaken. Where to go? Maybe it's not here. Yep, there. Specific heat capacities. So there are a couple of them listed here. And actually, water is right there. So 4.18 is the value that's listed here. 4.184 is what they were using in this text. So it's just a slightly different number of decimal places. So, but same value. When we talk about that, we can then say that since that's 4.184 joules per gram degree C, and we know that the temperature change is 23.17, the final minus the initial 22.50, then that gives us that 280.3 joules were picked up by that water. That's what was picked up. Okay, so if that's what was picked up, I know that that's true for my Q for PB. Okay, so if we change the sign on that, that becomes negative 280.3 joules. That's equal to the 26.47 grams times the specific heat times the change in temperature for that material. So again, when we're looking at that, that's that 23.17, or sorry, 23.17 minus the 89.98 that it started at. So since this is negative and this is negative, that means that the S comes out to be 0.158 joules per gram degree C. Okay, so once you've solved for S, that's what you come out. Okay, so it is possible to solve for a specific heat knowing this. It's possible to solve for any number of these values based on the information that you've been given using those equations. Okay, so looking to see useful equations. I don't remember if there's any of that in here, and I don't know if it is. I don't think it is. I typically don't ask about this on the test, and I'll be honest, it's because it's a lab thing, so I don't typically ask about it in the exam. But in the event that you're asked to solve for this, you will be given that equation. Okay, so you would be given this equation right here. So questions about that? So that is the kind of thing that you're going to get asked to do in that lab for the calorimetry. All right.
I'm sorry. Is the specific hit, like, is that going to be listed too? I'm sorry, I totally missed that. I was trying to do something.
So the ones for certain things they are, yes, and they are
Okay.
right here. So, but not all of them. No.
Okay.
So if I'm asking you for solve for one, it won't be in them.
Okay. Thank you.
Yep. So other questions about the calorimetry stuff? Now, the calorimetry that you're going to do, the virtual lab, is a little confusing because you have to take a lot of things into account because you have to find the Q for the calorimeter as well. So you'll need to make sure that you follow the instructions that are given in the lab. So in the lab, at the bottom of the lab notebook page, there's a little paper clip that says how to do these calculations. Make sure you follow those instructions. It is expected that you have those instructions with you when you do the post labs. So you are allowed to use those, the follow through with those calculations for the post labs that you do. So that is the expectation, because you shouldn't have to memorize that. Why? So you can have any notes that you took during the lab or anything that you use during the lab when you're doing it. Okay. So questions about that? Okay. Now, when we talk about standard enthalpies of formation, so I showed you some values for this in the last lecture that we talked about. Those were those delta H naught F values. And what delta H naught F means, it's a change in energy. That's what the delta is. Delta is for change. H is for, the enthalpy. The little circle like this means standard. So it's under standard conditions, 25 degrees, 1 atmosphere, those kinds of things. And the F, that little thing at the bottom, the F is for formation. So that's what all of that breaks down to. So it's the standard enthalpy of formation. Enthalpies of formation for a material in its standard state. Its standard state, meaning 1 atmosphere, and formation refers to the element in its most stable form. Those will all be 0. And we talked about that based on what we saw in the table last time. So O2 gas at 1 atmosphere and 25 degrees is 0 because it's most stable form. Anything that's not in its most stable form will have a value comparative to whatever it started as. So O2, if it's converted to O3, has an energy associated with that. Okay. So the standard enthalpy of formation is the heat change that results when 1 mole of that compound is formed from its elements at a pressure of 1 atmosphere. Okay. Those values can be tabulated and are shown, and it used to be shown on the exam handouts, and I apologize because I've taken them out of the exam handouts. Where is that? So they used to be there. Any values that you need, you will be given. Okay, so if it's not a 0 value and you need it, you will get it. It will be somewhere in the test. We can use the standard enthalpy values to determine the enthalpy of formation of other materials using the equation that the delta H for that material, delta H not F, is equal to the sum of the number of moles times the heat of formation for the products minus the sum of the number of moles times the delta H naught F for the reactants. Okay, so that's what this part means here. So again, this right here means sum. N is the number of moles. Delta H naught F is the heat of formation. And then we do products minus reactants. Okay, so it's always this stoichiometric coefficient. We have to multiply by the number of moles that we have to take into account the amount of energy we need for that number of moles. So as we saw in some calculations that we did last time, if we had 2 moles, we had to multiply by 2 for each of those. Okay, and like I said, we did that in the practice from the last lecture. Okay, but this is what we're looking at. So if we're doing it from the delta H naught F values that are tabulated, we always have to write the balanced equation to see what the stoichiometry is, and then do products minus reactants. Okay? All of the calculations that we will do for the next couple of lectures, delta H, delta G, delta S, all will be this same format. So it's always going to be the sum of the number of moles times the energy, whether it's enthalpy, entropy, or free energy for the products minus the reactants. So it's always going to be like that. Okay. So that's how we do our calculations for those. Now, given this table again, we can do some additional practice with this. What is the energy to make 1 mole of diamond from graphite? I want to do that. It's always my product. So I'm taking G, which is graphite, C, which is graphite because it's carbon in its graphite form, minus the, and then that gets converted to the diamond. And there's energy associated with that. So, I mean, this thing is a solid. We can reconfigure it from the graphite form, which is actually a whole bunch of carbons that are bound together in sheets, but the sheets are not bound to each other. So if we then bind them into the diamond form, those sheets are then bound to the other sheets, and that makes them incredibly strong. So that's what a diamond actually looks like, is it has bonds in every direction as opposed to just the sheet direction. So that's the energy that we're talking about. Now, since our product is a C diamond, that energy is right here, and it's 1.90. We're talking about 1 mole, and that's for 1 mole of this material. So that's my product minus the energy for the graphite, which is 0. So that energy is 1.90 kilojoules. And since it's 1 mole, we'll do it as a per mole. Okay. And so I've taken those values that were in the table and done that calculation. If I want to look at the heat of formation of N2O4 from NO2, so I'm taking N2O4 as the product that I want. I want to make that from NO2. I know that I need to take 2 NO2s to make it N2O4. Okay, so if my product is the N2O4, I need to see if I can find that N2O4, which is over here. So I have my N2O4, which is 9.66. 9.66 kilojoules per mole. And that is 1 mole of that material. And I subtract 2 times the energy for the NO2. And that NO2 is given right here as 33.85. And this is, of course, 2 moles. So if I do that happy math, assuming I can find my calculator again, at 9.66, and I subtract from that 2 times that 33.85, it gives me negative 58.04. And that would be in kilojoules. Now, I know that I'm doing that for this particular reaction, so I know that is a per mole of N2O4 formation, but I don't have to list it that way. As long as I'm calculating the energy for that reaction, I can leave it as kilojoules. So whether or not I choose to put it as kilojoules per mole determines it's just based on how I choose to look at this. So reporting it as either just kilojoules or kilojoules per mole is fine. Okay. So what is the heat of formation of liquid water from H2 and O2 gases? So in this case, I'm going to take H2 gas and react that with O2 gas to give me an H2O liquid. And it's important that I have those phases when I talk about what it is that I'm doing, because if I don't, then I might calculate it. Right? So what I mean by that is that my H2 gas, I come over here, H2 gas is 0. My O2 gas, where the heck is it? Oh, O2 gas is 0. But my H2O as a liquid is negative 187.6. And if, oh, that's H2O2, sorry, is negative 285.8. But if I was doing it in the gas phase, that's a different value. So I need to make sure that I've specified which phase it needs to be in to make sure I do the calculation correctly. So again, this is 0, this is 0, this value is negative 285.8. And again, those are all kilojoules per mole. So product, negative 285.8 minus the reactants, 0. Plus 0 because I just like to be explicit about showing it. And again, that's going to be negative 285.8 kilojoules, which makes absolute sense to me because the value that's in the table should be the energy that it took to make this thing from its components in their standard state. So if I'm making it from H2 gas, which is how H2 should be, and O2 gas, which is how it should be, then that energy that's in the table should be the value that I calculate for 1 mole of that material. Okay? So
Wouldn't there be 2 moles of water? Like, because you gotta do stoichiometry first.
Actually, that makes total sense. It's like that. But when I do that, and excellent point, thank you. So I end up with this. So if I was looking for this particular reaction, you are correct. 571.6. But if it had asked me what is the heat of formation for 1 mole of liquid water, then I would have to divide this by 2. Because then I'm forming 2 here as opposed to 1.
Right. Okay.
Does that make sense?
Yep.
So yes, the reaction as written would be for 571.6. If you wanted to do it for 1 mole of water, you would have to divide that 2 because you made 2 moles of water there. Now this next question asks for the heat of formation of liquid water from H gas and O2 gas. So again, looking at that, if I have H gas plus an O2 gas, give me H2O liquid, I need to have 2 of those, and I need to have 4 of those to do that. This here is 0. My value for the H2O still is that 285.8. And the H, so as we discussed, is the 218.2. So product 2 times the negative 285.8. This is kilojoules per mole, and this is moles, minus my reactants, so 4 times that 218.2. Plus the 0 for the O2. Okay. And so looking at that particular math, I have that 571 that I calculate for my product. And then I need to subtract from that 4 times the negative 218.2. And that gives me 301. So that's 301.2 kilojoules for this reaction. And again, that's for the formation of 2 moles of water under these conditions. If you wanted it for 1 mole of water under those conditions, you'd have to divide that by 2. Okay? And the energy is different because it takes energy to break those H bonds before you make that water. So,
Okay, I'm very sorry. I think for the H was the positive number, so that would have been negative 571.6 minus 4
you're
times the positive number.
subtracting, you're subtracting the negative number.
No, I get that, but the number for the H is the positive, so you would be subtracting from a negative number from a negative number, so you would be adding them
Oh, I put it
together.
sorry. Yes, I put a negative in the calculator. I apologize. Yes, that is my bad. So hold
Okay,
on.
okay. Because I was like, I got a different number.
No, it's because I put a negative there and it shouldn't have been there. So yes, negative 571. That is my bad. This is why I can't. My calculator cannot be trusted. We've discussed this. Yeah, signs are important, and I screwed it up. So. But yes, the signs are incredibly important when you do these calculations. And yes, I am often bad at that. So, does that make sense? I apologize for the mistake.
No.
So learn from my mistake. Don't do it. So again, that's all we have to do is to make sure that we're always doing our products minus the reactants. Okay. So any questions on that? Now, what we've been doing so far is called the direct method. And that's when we are able to use values from the tables that we know. But we can't always do that. Sometimes it's just not possible for us to measure what the heat of formation for a specific species is. It could be that reaction is really, dangerous for us to do. It could be any number of things that mean that we cannot do that. In that case, we have to use something else. And the process that we use is called Hess's law. And what it says is that the reactions are converted to products. The change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So if I can get a series of steps that I know the delta H for, where if I add them all up, it's the reaction that I want, then that will give me the energy that I need as long as that's what I'm doing. So if I wanted to know the enthalpy for C graphite plus half of an O2 goes to CO, then this reaction also produces CO2. It's not useful to determine the enthalpy that way because I get more than one product, right? So there are other ways that I would have to go about this. the way that we talk about this, if it actually will ever change, come on. There you go. So it'll come back. I'm sorry, there's a slight delay. So the indirect method, I can use the C graphite plus O2 goes to CO2, and that has a delta H for the reaction of 393.5. Okay, I can calculate that directly. And then I can get a COG plus half of an O2 goes to CO2 with a delta H of negative 283. Now, if I reverse the second equation and I add those two things together, the CO2's cancel, right? So if I turn this around and I get the CO2 goes to CO plus half of an O2, and I add those two things together, I get C graphite plus half of an O2 goes to CO as a gas, okay? So that cancels all of the other stuff. The value for this we measured as negative 393.5. And the value for this was 283, but we've reversed it. So now it was negative 283. So we've reversed it. Now it's plus 283. We add those two things together, and that then gives me this negative 110.5 that I see right here. Okay. So while I cannot do the reaction directly the way that I wanted to measure it, I can use two other reactions that I know values for to get that reaction energy. Okay. Now, when would you have to do this? When I give you something like this on a test. That's really what it's about. Okay. Now, there are times in practicality when this is something that has to be done. So this is something that's useful to know. And so that's why we're asking you to learn how to do it. Because there are times when we don't have a value for a specific thing that we're looking for, a type of reaction. We cannot measure that directly, and so we have to measure it in an indirect way. Okay? Now, does this process make sense? And what you would see if you were asked to do this is exactly the kind of thing that you see right here, is these two things. And then you would get, hey, I want to know what this type of reaction is. How do I use this information to get this? Okay. So that's our direct method versus our indirect method. So here's another example of something that you might see. So these are the reactions that you've been given, right? And one of the things that I might be asking for is, what was my plan with this? Now, okay, so I might be looking to see what the energy is to take Fe2O3 Well, I already have that. Well, that wasn't helpful. Oh, these are two different types. I'm not sure what I was doing here. And I don't know why it doesn't say. I hate it when I do this. Give me a sec. This one at least has a question. If the reaction of acetylene C2H2 with hydrogen H2 can produce either ethylene or ethane, what is the delta H for the reaction of C2H2 with H2 to form C2H6? So I have information about what happens when I react C2H2 with H2 to make C2H4. And I have information about C2H2 plus 2H2 to make C2H6. But I want to know, what is the reaction? That's the energy I'm interested in. And so the question becomes, can I use the information that I've been given to do this? And the answer is yes. Okay. So how would I manage that? Well, I know that I want to start with C2H4, right? So if I want C2H4 as a reactant, I need to reverse this reaction. So if I reverse that reaction, I have C2H4, and that goes to C2H2 plus H2. Energy for that would be 150 or 175.7. Okay. I also want C2H6 as a product. So if I use this reaction as written, I should be able to get C2H6 as a product. So I would have C2H2 plus 2H2 going to C2H6. And that energy is negative 312.0. Now, if I were to add these two things together, the C2H2 would cancel, this H2 would cancel, and I'd be left with one H2 there. And so I would end up with C2H4 plus an H2, giving me C2H6, which is what I was asked about. And so if I were to add these two values together, that should give me the information that I was trying to get at. And that gives me a net of 136.3, which is negative. So that's the energy associated with that reaction. Does that make sense? And again, I looked at the information I was given and I said, okay, C2H4 needs to be a reactant, so I'm going to flip that. C2H6 needs to be a product, so I'm going to leave it where it is. And then I just added them to see if that was the reaction that I needed or not. And if it wasn't, I would see what I needed to do to make it the reaction that I need. Because the stoichiometry might be wrong. I might need to divide it, something like that. But as long as I have the reactant that I need and the product that I need, and I'm close, I should be okay. I should be able to get what I need out of it. So does that make sense? Okay. So things for the exams that you might need to know. You might be asked about both the direct and the indirect method of determining delta H. Both of those things can be things that you'll see. I would expect one indirect and probably a number of different types of direct. You'll probably need to know that most of the stable forms of delta H are zero. So anything that exists as it is in nature would be zero. And those won't be included on the tables that you'll get because it takes up space and there's no reason for me to list it if you should already know what it is. What that means is that a number of things, you'll need to know what their common states are. So O2 gas, N2 gas, H2 gas, F2 gas, Cl2 gas, Br2 gas, Br or I2 not as a gas. And actually, two of those are wrong. This should be a liquid, and that should be a solid. So this is liquid, in its standard state, and this is a solid in its standard state. So both of those would be 0 as well. C as the graphite form. Now, other things that you may not know, like the S in whatever form it's in, so the monoclinic is the standard, that would be on the table. Okay, but things that you should be aware of, any of our diatomic gases, Br2 is a liquid, and I2 as a solid. So all of the halogens I would expect you to know, and then our other things that are normally gases. So. And again, you should be able to explain why it's a 0 value, and that's because it's how it's in nature, so we can't measure anything other than what exists. So we can only measure energy differences, not absolute values. Right? So that's something. Cool with that part. Questions, comments, problems so far? And the other thing we're going to talk about right now is phase changes. And that's because we never talked about the energy changes that that are associated with phase change. So we've talked about all the phase changes, what those names are, what that looks like. Okay. So if I go from solid directly to gas, that is a sublimation. If I go from gas directly to solid, that's a deposition. Going from solid to liquid, we list as melting, liquid to gas is vaporization, gas to liquid is condensation, and liquid to solid is freezing. So we know all of those terms, but there is an energy associated with all of those terms. Okay. So that's the enthalpy of those phase changes, right? Now, you are not going to need to know how to calculate those energies, but you need to know that there is a molar heat associated with all of these things. So that's the energy to do this to 1 mole of material. So if I'm going from the liquid to the gas phase, that's the molar heat of vaporization. Okay. If I'm going from the gas phase to the liquid phase, that's the molar heat of condensation. Okay. And it is listed as a delta H and then, a subscript to go with it. And it's the energy required to move 1 mole of material between those two phases. Okay. The other thing you need to understand is that if we're talking about going directly from a solid to a gas, that is the same as it would be taking the solid from the solid to the liquid and then adding the solid to the vaporization. So that vaporization process. So I can add those two energies together to get the one for going directly between them. Okay. So those energies should be available to you on the test. You can work with them in any way that we typically work with these delta H's. There is a way to calculate what these values are. I will not ask you to do it, but there is a way to calculate. Okay. So is anybody unclear on the energies associated with the phase changes? So going one direction will be positive, going the other direction will be negative, just like we've talked about for other things. Okay. So questions on our phase changes? So what conditions must be met for heat of formation to be standard? Well, it needs to be at 25 degrees C. We need to be under 1 atmosphere of pressure. And we're talking about 1 mole of material. So that's a standard heat of formation. All right. What is the standard heat of formation for O2 gas? That is listed as 0, because that's how we find it in nature. What is the standard heat of formation of O2 liquid? Would it be the same as for O2 gas? No, because it's going to take energy to take it from the gas phase to the liquid phase. So those would not be the same. Okay. I can calculate delta H for the reaction of C2H2 plus H2 going to C2H4, given the information that is listed here. Now, the question becomes, how would I combine those equations to give me that reaction? So I see that C2H2 here is on the correct side, but is not the correct stoichiometry. So I will not need to flip this equation to get C2H2 on the right side, but I'll need to cut this in half. So I would have C2H2 and of course this energy would then be negative 250 divided by 2. I'm not going to do the math. Oh, what the heck? Come So again, not actually doing the math, but I would have to divide that by 2. Okay. If I want to have C2H4 as a product, then I would need to flip this reaction right here. So I'm going to flip this around. I would have 2 CO2 plus 2 H2O. It's a liquid. This is the gas. C2H4 as a gas plus 3O2. And that would have a value of plus 141019. Okay. So that's that. Now, I know that this probably does not give me exactly what I need. And I'm saying that because there is this other equation that they gave me. So I'm going to add these two together to see what I end up with. Okay. So I'm just going to add these two equations to see what I get. I have C2H2 plus 5 halves of an O2 plus 2 CO2 plus 2 H2O. That gives me 2 CO2, and no, I have not canceled anything, plus an H2O, plus C2H4. So since I have a CO2, 2 CO2s on both sides of these equations, I can cancel those two. I have an H2O on this side, and I have 2 on this side, so I can cancel that. That leaves me with 1 H2O there, and I still have that 5 halves of the O2. Okay, so I know this isn't quite right, but I do have this other equation that's been given to me that has this H2 here and the half of an O2 and the H2O, right? So I can use that by adding it with the other ones. So if I add that up here, H2 plus the half of an O2 to give me an H2O, and I do that, which is that negative 285.8, if I do that, then I end up with the H2 being added And then I get half of an O2 plus that 5 halves of an O2 gives me 6 halves, which gives me 3 O2. And I have an H2O on the product side that should go there, but it can cancel with the one that's here. So that gives me that equation. And unless I've canceled something incorrectly, which maybe I have, I don't know. Let me check. Well, I end up with an O2 in there that I wouldn't have expected. That's interesting. Oh, did I forget? Oh, I did. So there was a 302 here that I needed to get rid of. And since I had a 5 halves, and I subtract that 3 from it. Brain not working. Gives me 2 there. And then with the O2 from that one, I still end up with O2. Okay, what did I do?
I think you're good on
That,
O2s because you
yeah,
get
I
2.5
did. What?
plus a half
Yeah,
minus a 3.
yeah. I just couldn't add, which is normal. So yeah, I end up with the 1/2 over here and the 1/2 over there. So I'm good with O2. That is correct. So that is what we needed. And so if I add all of those values together, I take the negative 285.8, I have the negative 259.2599.2 divided by 2, and the 1410.9. If I add all of those together, that will give me exactly what I need. So cool with that.
Yep.
Yeah. We can calculate the enthalpy for formation for benzene, C6H6, given the heats of formation of CO2 and H2O, and that the heat of combustion for C6H6 equals negative 3267.7. So again, I'm looking at a couple of different things. So I want to find that C6H6 formation. So C6H6 liquid. And I want to make that from the materials that make it. So we're talking about like carbon graphite plus H2. Okay? And of course, I would need to have 6 of those and 3 of those to do that. So that's the energy that I actually want to calculate, is for that reaction. Okay? So that's what I've been asked for. If I know the heat of formation of CO2 and H2O, okay, then, and I know the heat of combustion of C6H6 and the reaction for C6H6, we take heat of combustion C6H6 plus O2 is going to give me CO2 plus H2O. I know I need 6 of those to make that happen. I need 3 of those to make that happen. And then, of course, if I do that, then I have 3 there, 12, 15. And so we would typically write this as C6H6. 2 of those plus O2 gives me 12 CO2 plus 6H2O. So that's typically the way that we would write that, so that we don't have fractions in that. If I know, it says write the balanced thermochemical equation that divides the enthalpy of formation of C6H6. That's this reaction right here. It's that thing they asked me about. At the balanced thermochemical equation for the heat of combustion of benzene, and again, that reaction C6H6 plus O2, that's the basis of that heat of combustion, which then gives me CO2 plus H2O, and that's this right here. Okay. And then based on our answers, we should be able to look at an expression for the heat of combustion of benzene in terms of enthalpies of formation of the reactants and products. So if this is the liquid right here, then if I know what this energy is, and this energy is, and this energy is, then I should be able to find, if I knew what the heat of combustion was, which I do, then I should be able to solve for this energy right here. And of course, the way that would happen is that I know that the delta H for the combustion has a value of negative 3267.7, and that is equal to the sum of 6 times the heat of formation of the H2O, which I was given as negative 285.8. And I'm leaving all the units off, I know it's terrible, plus this 12 CO2, which again I was given as negative 393.5. And then I would subtract from that the heat of formation of my starting materials. So 2 times whatever the value for the C6H6 liquid is, plus 15 times 0, because that one is a 0 value. And so if I do all of this, I can solve for that X value to get that heat of formation for C6H6 using that. And that's what they're walking you through, is how you would plug all that stuff in to be able to solve for that X. Okay? So questions about that? And I will do all the math and post that in just a little bit because we're over. So this one I can post as well. And that is actually, I think, the last. Yep, that is the last one I have. So are there any questions about what we talked about today? Any questions about any of the materials for the test? Anything at all? Okay, the test is available. It is open. You have until end of day Monday to take it. So based on what happened today, we do not need to meet for lecture on Monday. But if you want to meet with me to talk to me about anything for the test, that is fine. Just let me know via email and I will be happy to do that. I will get these posted and I will get this lecture posted and then we should be good to go. And I will do everything I can to have this the test graded by Wednesday. So.
Thank you.
All right,
Have a good
guys.
one.
Have a great weekend.
Bye.
See ya.